For centuries, there were only two ways to do astronomy. You could theorize, or you could observe. But in the last few decades, a new branch of the field has emerged. Now, using computers and an understanding of the laws of physics, you can simulate. And to the extent what you simulate ends up looking like the real universe, you can gain tremendous insight into how what you see in the sky came to be. We're watching a simulation that begins 12 million years after the Big Bang and runs for 13 billion years, basically up through the present time. At the beginning, we are seeing how the density distribution of dark matter creates the foamy texture of space-time upon which galaxies will grow. We can see clusters of those galaxies, connected by long arcing filaments, which encircle large voids containing hardly any organized matter. Astrophysicists can make out this general arrangement very clearly in maps of the cosmic background radiation left over from the Big Bang. But what we're watching here is a new simulation that for the first time accurately models not only the web-like structure of galaxy interactions, but also conjures up the correct mix of spiral, elliptical, and irregular galaxies. And it shows how, when, and where every element more complex than hydrogen or helium was created. We're watching now the temperature as matter under gravity heats up. Blue marks the coldest areas. Greens are warmer. Whites are, well, white hot. As more stars condense out of cold gas, an evolution in their types develops. Astrophysicists talk about elements with more and more electrons as being increasingly metallic. Supernova explosions produce higher and higher order elements, some of which are then collected and upcycled through later generations of supernovas. And the metallicity of the surrounding space increases. We can also detect in this data the fruition of supermassive black holes at the cores of large galaxies. Now here, we watch some of the earliest galaxies in swirling interaction over billions of years. The view in normal starlight is on the left. But on the right, we can now watch the gas density of the same events. This is how spiraling galaxies disrupt one another on their way to joining together to form a giant elliptical galaxy. Now we watch the goings-on within a cube of space. Both sides show the same region. But on the left, it is as if we've put on a pair of special glasses which let us see dark matter by its density variation. On the right, we're watching the gas temperature of normal baryonic matter. And that flickering is the product of active galactic nuclei cycling through their quasar phases. The software engine that produced these simulations is named Illustris. A team headed by Mark Vogelsberger of the Massachusetts Institute of Technology developed it. They attribute their success to access to lots of computing power, to the availability of clever new numerical algorithms, and to recent advances in the understanding of the physics of dark matter and normal baryonic matter in and around the centers of galaxies. To check their results, the team created models of the distribution and types of galaxies found in the Hubble Deep Field, Extreme Deep Field, and Frontier Fields image data, then compared what Illustris came up with to them. A representative mix of spiral and elliptical galaxies, very much in line with what astronomers see on the sky, has been created. The result is what's being touted as the most accurate predictive simulation of the structure of space yet made. With this finding, astrophysics by simulation has clearly come of age. For Space.com, I'm Dave Brody, and if you have a question, tweet me at David Sky Brody. Space.com